Hello, we are Projekt Scorpio, part of Scientific Society Off-Road, based at Wrocław University of Science and Technology. Right now, we have 29 members from multiple disciplines. Our workflow is divided into 4 departments: mechanical, electronic, software, and science. Each department is responsible for different aspects of our rover. Scorpio X rover is based on simplified rocker bogie suspension, connected with differential beam. Main body of the rover is made using lightweight materials such as aluminum or polyamide. Our driving module features all-wheel drive with special kind of Cortura tires. As for the robotic arm, it has 6 degrees of freedom and it can lift up to 5 kilograms of maximum extension. Robotic arm can take soil samples by exchanging tips of the gripper. Driving module is equipped with kill switch that cuts power from batteries in case of emergency. Every PCB has overvoltage, overcurrent and undervoltage protection, as well as overvoltage clamping. Vision systems consist of 5 cameras. First one of them is our navigation camera. It is capable of rotating in 2 degrees of freedom. Second camera has ultra-wide lens and is mounted on the front of the rover. Third camera is a stereo camera mounted on a second mast. Fourth and fifth cameras are mounted on the end of the robotic arm. We use 2 types of communication buses in our rover. First of them is Ethernet connection link between our base and the rover. Second one, CAN bus, serves as main data link within the rover. It connects our main computer, NVIDIA Jetson TX2, with every sub-module. To connect with the base, we use 2.4 GHz and 900 MHz frequencies. Software is divided into independent fault-tolerant modules which can exchange information via our message broker by TCP/IP protocol. Navigation module is responsible for processing telemetry data from GPS, IMU and visual odometry. Robotic arm control system allows us to implement many types of control in tasks or configuration space. We use web application on board the rover which collects all data, for example sensors, position or drive parameters. We can present results in form of charts, tables and reports generated in real time. To tackle with science tasks, we provide our rover with numerous sensors and DIY devices that allow us to conduct chemical analysis. All data are measured on board the rover. Results are analyzed in our base to characterize ambient environment. Sensors capable of constantly measuring environmental parameters like temperature, UV index, humidity are located on the mast. Soil samples are placed with robotic arm in special rotary container, Universal Land Exploration Platform, ULEP. Thanks to that, we are able to separate samples from different sites, some chambers containing chemicals necessary to characterize the soil. ULEP is completely isolated. Any chemicals or water used on board are saved and will not spill on the ground. Sensors capable of measuring soil parameters such as pH, humidity, microscope and spectroscope are placed on another descending rotor which analyze each sample in ULEP. Our rover can cross extreme terrain thanks to suspension system, very low center of mass and exceptional tires made from Cortura. Our rover can overcome obstacles up to diameter of the wheel and vertical cliffs up to 1 meter. In order to speed up target finding, we designed Augmented Reality system. Every task target has its own marker on navbar and self-orienting map. We made some improvements to our robotic arm from last year. We redesigned electronic boards to make them cheaper and more robust. We use combination of worm and harmonic gear reducers to maximize precision and stiffness of hull construction. We achieved that with use of very light and durable materials such as carbon fiber tubes, aluminum and PETG. Gripper gives us satisfactory grip strength and precision. In order to complete all necessary subtasks, we decided to mount Allen hex key and small linear solenoid on the end of the effector. For precise typing and operating joystick, we will incorporate 3D inverse kinematics. Main sensors used in autonomous traversal task is stereo camera, differential GPS and inertial measurement unit. Based on depth map from stereo vision, we create visualization of real terrain. Based on rover forward kinematics and terrain map, we implemented high-fidelity traversability analysis algorithm and path planning based on A*. To estimate wheel sleep, we use differences between wheel odometry and visual inertial odometry.